Our primary goal was to focus on a turbine that generated a maximum amount of volts in comparison to how fast the blades spin. We decided that the most effective way to accomplish this goal was to focus on creating an efficient cost-to-performance ratio, while still reaching numerous stretch goals. We felt that by focusing on the gears, structure, and lighting an LED, we could successfully construct one of the most effective turbines. Immediately, we began by sketching out numerous designs. Our designs ranged from the complex and expensive to the overly simplistic and cheap. Finally, though, we chose a design that was somewhere in the middle. A pinwheel design is tried and true, so we knew that at the very least it would spin and generate power. We also understood that the cost would be low, as there are very few necessary materials. In fact, most of the cost would be invested in 3D printed parts, such as the gears and a core hub. In addition to the gears, we saw the opportunity to complete several other stretch goals. Our design included a solid base, which would be sturdy enough for us to disregard the use of a C-clamp, a manual stopper, and an opportunity to add more than 4 blades. Our original turbine device was a construction paper pinwheel attached to a cork. The cork was then inserted into the motor, and we ran some tests to see how many volts this simplistic design would generate. After thorough testing, we found that on average, this iteration only generated 0.04 volts. This was well below our output goal, so we needed to change things in our next iteration. Iteration 2, we decided to experiment with adding multiple gears in an effort to convert the kinetic energy generated by the spinning blades into that of electrical potential energy more effectively. Next, we realized that with numerous motors we could quadruple the output of power quite easily. This led to our second iteration, which, while similar in appearance to our first design, is not exactly the same. Our second iteration was significantly better. It incorporated 4 motors, 4 blades made of paper, and 3D printed gears. With these improvements, we nearly doubled our energy output, producing 0.07 volts. For our third iteration, we chose to try different materials for the pinwheel to see if they were even more effective. We chose the polycarbonate plastic as a result of it being lighter, stronger, and larger in radius than the paper we had been using. This had a slight impact, as our third iteration generated only 0.11 volts. Finally, we introduced our final design, a turbine that incorporated 8 blades, 5 gears, and 4 motors in series. Our final device stands at 61 centimeters tall and can be disassembled and put into our box with ease. The base and primary support for our device simply consists of a 1/2 inch wooden dowel coming up from a Martian rock we drilled a hole into. From there, we have our first 3D printed element. We created a housing device that would hold our gears, motors, and pinwheel together in a compact way. Each motor has a small gear with 12 teeth that turns as the large 100-toothed gear rotates. In addition, there is a 75mm nail that goes through the device and 2 bead bearings that holds the pinwheel up. Lastly, the pinwheel blades themselves are made from the previously mentioned polycarbonate plastic. This final design cost about 132 spaceship parts in total. The first 20 space bucks we spent went towards using the communal tools. Next, we spent 32 space bucks on our first iteration testing. We purchased 4 feet of 1/8 inch wooden dowels and 6 sheets of construction paper. For our second and final iterations, we did a lot of 3D printing, which came out to around 25 space units in total. Finally, we purchased a nail, a Martian rock, and 10 beads, which, combined, cost an additional 30 spaceship parts. Our final purchase was the 2-foot by 4-foot sheet of 1/1000th inch polycarbonate plastic from McMaster. In total, we used less than half of our original budget of 275 space bucks to complete our device. Our wind turbine ended up being one of, if not the most effective on Mars this year. Our final design generated at most 20 times more power than our first iteration. With 8 plastic blades, 4 motors, and 5 gears, it was able to generate a maximum of 0.8 volts. This, however, all depended on the angle and speed of the wind. For our official test date, we generated 0.5 volts as well as 0.3 milliamps, meaning our final turbine design produced 0.15 milliwatts in total.